In this lesson, we're going to talk about instantaneous rate of change. In Chapter 1, we talked about an average rate of change, and now we're wanting to take a look at what happens from average rate of change when you start looking at a very small interval. As a quick example, if you drove 180 miles and you did that in a 3-hour period, what was your average velocity? Remember, velocity was distance over time, so this one is really nothing more than doing this 180 miles divided by 3 hours, and that's 60, which would be in miles per hour. Now for this example, we're looking at a ball that's thrown in the air, and we're looking at its height in feet. We want to get an estimate for what is the velocity of the ball at exactly 1 second. Exactly 1 second. Not the average, but the actual speed of the ball at 1 second. We know the height of the ball, but not necessarily the velocity of the ball. Here's the strategy that we're going to take. From t equals 0 to 1, we'll look at the average velocity in that time period. You have 90 minus 6 over 1 minus 0 is 84 feet per second. And then we'll look at the right side. For t equals 1 to 2, we'll do 142 minus 90 over 2 minus 1. That gives us 52 feet per second. Now what do we do with this? If we want to know how fast the ball was going at exactly t equals 1, then our best guess would be just to average the two. Let's take 84 plus 52 and divide it by 2. That gives us 68 feet per second. Now let's take a look at this a little bit further. If we were actually to be given an actual model for what we were just looking at, we would have been given this formula. Y equals negative 16t squared plus 100t plus 6, which is a pretty standard model for position of an object in free fall, on the Earth at least. If we were to make a table of values, and instead of having 0 to 1 to 2, we had the 1, but we also had something closer. 0.9, 0.99, 0.999. And same thing on the right side, 1.1, 1.01, 1.001. If we get closer and closer and calculate the average velocities on that time period, that should give us a better idea. Notice on 0 to 1, we still have the 84 that we found. On 1 to 2, we still have the 52 that we found. But then from 0.9 to 1, we've got a much closer value to the guess that we had. On the other side, it's a little bit short of that value. And by the way, if you average these two together, you're going to get 68 again. Get a little bit closer with the 0.99 and the 1.01. That again gives us numbers that are even closer to 68. And then when you do 0.999 to 1, you'll notice these values even to one decimal place are now exactly 68. Now this is actually only in a quadratic where you get the exact answer without having to zoom in, but we actually did find the exact answer. The ball was traveling at 68 feet per second at t equals 1. This process that we just described is what we call a limit process, of taking smaller and smaller intervals and considering something you're trying to calculate. So what we'll define is the instantaneous rate of change of a function at some point A. Sometimes we'll just call it the rate of change rather than the instantaneous rate of change, not to be confused with the average rate of change. To get this, we'll look at the limit of these average rates of change as we make the intervals around A smaller and smaller. And then the instantaneous velocity would just be that instantaneous rate of change for the position over time. Same idea as what we did with average velocity, with distance over time. Let's consider a numeric example of this. What if we want to estimate the rate of change in a function if t equals 3? The data is no longer given as a table, it's given as a function. So what we'll do is compute the average rate of change on 3 to 3.001. This is the strategy we're going to use in general. A great estimate of the average rate of change is if you start with the t value you're looking at and move up some very small increment, and we'll always use t equals 0.001 for the increment unless a homework problem says otherwise. Keep an eye out for that. So if we're computing the average rate of change, I'm going to treat this like my a and this like my b. And I'll plug my values into my function, which is this q here. Here's what it looks like after we plug in our values. F of b, we plugged in 3.001 into the function, minus f of a, we plugged in 3 into the function, over b minus a. This comes out to approximately negative 2.86 milligrams per hour. So after 3 hours, this is the speed at which the quantity of the drug in the bloodstream is changing. After 3 hours, the drug is leaving the body at 2.86 milligrams per hour. Notice I changed the negative number to a positive number and said it was leaving at that speed. Now, this is one of the biggest concepts we're going to be working through in this class, called a derivative. So the derivative of a function we will often write with this notation. F prime of a is how it's read, and f prime of a is the derivative, which will actually show to be a function in the next section. And f prime of a given point is simply defined to be the instantaneous rate of change of the function at that given point. Let's do an example. For this function, f of x equals x cubed, let's estimate the value of f prime of 2. So first off, what does that mean? If I rewrite this, what it really means is we want to find the instantaneous rate of change of the function at x equals 2. And now we'll do this just like we did the last problem. We'll make our estimation by going from 2 to 2.001 on the average rate of change. And like I said before, that is the increment, always 0.001. So we're looking at f of x is equal to x cubed. So f of b would be 2.001 cubed. F of a would be 2 cubed. And then we have this over b minus a. If we calculate this, we get 12.006001. That's our exact answer, but in all actuality, I'm just going to go ahead and mention that this is about 12. And the real answer when we're not estimating would actually be 12. So we'll talk about that in a later section. Here's a visual for how the derivative actually looks on a graph. The average rate of change we talked about previously was like a secant line. So if we take a look at that secant line and we start shrinking, we start applying this limit process. As these 2 points get closer and closer together, the lines start to get closer and closer to some line that touches the curve in one place and moves in the direction of the curve. We call that a tangent line. And so the derivative of a function is equal to either the slope of the graph, which I'll talk about a little bit more in a second, or you can consider it the slope of the tangent line at that given point. Now what do I mean when the slope of the graph? Well, if you take any graph whatsoever and you plug it into your calculator, and then just start zooming in and zooming in and zooming in, you'll discover that as you zoom in far enough, the graph looks like it's turning to a flat line. So these examples show some random curve, and if we were to take this little circle and zoom in, it would look a little bit flatter. But then if we take this little circle and zoom in again, after you've zoomed in twice, the graph looks practically flat. That is the slope of the graph. Let's see if we can do some estimations. Use the graph of f of x equals x squared to determine if the following quantities are positive, negative, or 0. F prime of 1 is asking about the instantaneous rate of change at 1. The instantaneous rate of change at 1 is the same as the derivative, which is also the same as the slope of the graph or the slope of the tangent line. This might be a good time to highlight the similarities. All of these concepts are actually the same idea. Instantaneous rate of change, derivative, and slope. Specifically slope of the tangent line or the slope of the graph. At f prime of 1, what that means is I'm going to look at the graph at 1 and I'm going to attempt to draw something that sort of represents the slope of the graph. It's nothing special, it's just enough to say, hey, take a look. That is obviously positive. Now let's take a look at negative 1. What that means is we'll try to draw the equation of the line at this point. By the way, we don't have a way to find these equations yet, but we can take our best guess. More so I'm going to be asking positive, negative, or 0 than I would trying to find an exact value. So then this one would definitely be negative. Now f prime of 2. Here's 2, which has a very high slope if we were to try to eyeball this. Again, this one is positive. Now this one, if we draw the 0, 0 point, it actually looks like the tangent line is flat here. So this would be a case where the slope was actually 0. Now let's do a comparison between the two. Let's take a look at the derivative of 2 to the x at x equals 0. Let's try to estimate it graphically and estimate it numerically. If I try to do it graphically, what I'm going to do is draw the tangent line the best that I can. Let me show you how to not do it. That way you can get a feel for what you should do. Here's an example of a tangent line that's not tall enough. You'll notice that it intersects the curve on the left side again. That should never happen. Here's an example of a tangent line that's too high. You'll notice that we've got this intersection on the right side. So if you're intersecting it on the left side, it's too low. On the right side, it's too high. And you want to find the place that gets it just right. This one's a pretty good representation because it looks like it only touches the curve once. If anything, it maybe could be a hair higher. So graphically, what we'll do is we'll kind of look at the points and say, here's another point on that line. I'm going to say the rise is about 2 for a run of 3. That's what we're looking at here. The tangent line has slope about 2/3, and I went ahead and approximated that to about 0.667. That will help us. Now for numerically, we'll use the 0.001 idea. So if I want to approximate f prime of 0 numerically, I'll do 0 to 0.001, plug it into the function, and calculate the average rate of change. If I do that, I get approximately 0.693, which was actually really close to our guess. Now, if you didn't quite get a good guess like that, it takes a little bit of time, and again, I'm not going to be asking a lot of questions along the lines of getting really exact values. Estimation with your eyes and just trying to draw the tangent line is pretty hard to do that accurately. Next, let's do a little comparison between the different things that we've done so far. If we're looking at f prime of 1, what that means is you would take a look at this point and then take your best shot at the tangent line that seems to follow the curve. That seems to be a pretty good one. We'll say the slope of that line is about 1. And again, that's exactly what I'm looking for, the slope of the tangent line. Next, f of 3 minus f of 1 over 3 minus 1 is actually an average rate of change. The average rate of change took 2 points and then found the slope of the secant line that passed between them. So I'll take a point at 1 and a point at 3, and then I'll draw the line that passes between those 2 points. This one looks like it is about -2/3. And again, that is the average rate of change, where we calculated the slope of that secant line between 1 and 3. Now the last one is one that's more coming from things you've done previously. f of 4 minus f of 2. f of 4 actually just means take the point at f of 4 and consider the y-coordinate. f of 2 would be consider the point at 2 and consider the y-coordinate. So then f of 4 minus f of 2, what we'll do is look at this little gap right here and find the difference in y values. This is actually what we call the net change, and it does matter what order as well. That number looks to be about -1.4. And the negative sign is important because you're taking a smaller number at this point minus a larger number at this point. This would be the value at 4 minus the value at 2. For our final example, let me show you a little shortcut that you can use when you want to take table data and find the actual instantaneous rate of change, or you can call it the derivative, at a given point. Here's the total farmland in millions of acres in the US since 1980 through 2000. For the first question, what is the average rate of change between these 2 points, 1980 and 2000? Remember, 1980 and 2000 would be your A and your B, respectively. And then if we do the average rate of change, we'll plug in our table values. 945 was f of 2000, minus 1039 is f of 1980, over 2000 minus 1980. If we do that, we get -94 over 20, which is equal to -4.7 million acres per year. That's the average rate of change. Now, the instantaneous rate of change, f prime of 1995. Here's a shortcut. In our first example, we took the values of an average rate of change between 1990 and 1995 and between 1995 and 2000, and then we averaged them together. That's a little too much work. Here's a shortcut that actually works most of the time. That's assuming that these things are equally spaced, and if that's the case, we can take the average rate of change with the number before and the number after. So in order to find f prime of 1995, the shortcut is to do the average rate of change from 1990 to 2000, and you'll actually get the same answer as if you had done two average rates of change and averaged them together. You might think about what those numbers would look like and see if you can convince yourself why this shortcut works as well. So in this problem, I have 945 minus 987 over 2000 minus 1990. When I do that, I get negative 4.2 million acres per year.